right, Syrian's group. How many valence electrons does nitrogen have?
5.
5. Very good. Who else saw there was 5? Hand raised. What is the electron configuration for nitrogen? And be quiet for me. Thank you. Let's go Ashton's group. Ashton's group. Electron configuration of nitrogen. Say again. Loud and proud. The whole shebang. I want the entire electron configuration. So if I say electron configuration, you should be thinking 1s blank. Okay, go for it. Keep going. 2p3. Perfect. I was trying to write that as you were going on my smartboard. Okay, so 1s2, 2s2, 2p3. Can you see the 5 valence electrons there, guys? Where are they? 2s2, 2p3. Okay, so you guys said there are 5 valence electrons. How many valence electrons does aluminum have? Aluminum. Look at aluminum. Shout it out for me.
3.
3. Aluminum's electron configuration is 1s2. What next? 2. Ooh, s2. Keep going. 2p6. Keep going. 3s2. 3s2 and 3p1. Where are the valence electrons? In the 3s, in the 3rd energy level. Okay, so can you guys now just look at the periodic table without actually writing down the electron configuration and tell me how many valence electrons every single representative element has? Everybody in group 1 has how many valence electrons? 1, because they all end at blah 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 S1. Okay, so everybody in group 1, hydrogen, lithium, sodium, blah blah blah, has 1 valence electron. Group 2, 2 valence electrons, because they end at what? S2. Skip over transition metals because they are weird. Go to group 3. How many valence electrons do they have? 3, because they all end at what? So S2, P1. And I'm just not saying the coefficient number because it depends on which level we're on. Okay, everybody in group 4? 4 valence. Everybody in group 5? 5 valence. Everybody in group 6? 6 valence. 7? 7 valence. 8? 8 valence. It goes in accordance with the group number. And so if you don't remember anything else, that is probably one of the biggest ideas of the patterns you see across the periodic table. Because what does periodic mean? There's a pattern. It's called periodicity. So if you say, I periodically go on a 5-mile run, there's a trend. There's like once a week or every Sunday. There's something about a pattern there. So that's what the periodic table is called, periodic, because it's got a periodicity associated with it. And in that case, the group number is the valence number. All right, so keep that in the back of your brain. Go to Unit 2 docs. There's a simulation there. You guys can write. I want you to write down some of the things you do. You don't have to do every single question in the order it is there. You can move around some. But when you click on the Unit 2 docs for trend simulation, it'll have a series of questions. It has a little a link that brings up another periodic table. And that periodic table, if I opened it twice, it's under Teach Chemistry. So you might need a friend to open up the periodic table while someone else pulls up the actual doc. So I'm going to give you guys about 25 minutes or so to play with this. Now you're going to make some self-discoveries, and then we're going to pick up from where we left off writing. Okay? So feel free to chat, talk about this, write down some of that information.
Give me a 0 on those 2 things. Remember I went through that one.
And I didn't write it down.
Yeah, problem set 4 and reading guide 5.
I gotta make sure I write down this because I don't see it. Can I hold this for a hot second?
Yeah.
Because I'll write it myself.
Problem set 6.
Okay. Alright, like I said, you might want to look on with somebody. I should hear you talking about the answers so that you guys are using your vocabulary, kind of keeping it real here. Don't write as much. You should be talking and writing. Yeah. So my goal is to help you learn instead of killing your brain with work. So that's why we're trying to do some easy play of using spiral cable trends.
Yeah, sure.
In pairs, yeah, that's fine. That's what, because it's easier if you have one person to talk, one person to the simulator. Yeah.
Number two, like it says, what subatomic particles would be found in the center? Would that be like protons and neutrons?
No, protons and neutrons.
So what is an alpha particle?
An alpha particle is a particle that's the size of a helium nucleus. It's got two protons and 2 neutrons. We're gonna get into alpha particles when we get to nuclear radiation tomorrow. Okay, it's a different kind of particle. You guys are doing great together. I'm loving the conversation. Keep it up. Of data you saw. So why do you think I did it this way? Why do you think I flipped and made you guys go through conversation first, and then now I'm going to pick up next? Right. Well, and I hope that as you guys have kind of planted about 5 or 6 seeds in your head, we can make that into one big tree. Okay, we can kind of pull that together in terms of clarifying some questions you may have or finding ways to connect the dots between those. Okay, so bear with me. I have some notes that are redundant, so I'm skipping those. You guys have this from Friday, yes? Nuclear effective charge. Okay, you want to pull that out? Yeah. Okay. All right, so if you were not here Friday, there's a really like 7-8 minute video of me walking through the differences with the periodic trends. So my goal is to hit the highlights, and then we're going to apply them more by finishing up and clarifying some questions on your problem set. So make sure your problem set's out and accessible as well. And as a game plan for the rest of the week, I know some of you guys like to know, I updated the website all the way through Friday now. I was trying to making plans because we had a half day, and then Friday we have, this coming Friday, we have homeroom for an hour during our intervention block, because ACT people have to do their pre-administration stuff. So that eats into our class time by about 10 minutes. So in order to not cause any stress for Unit 2, what I said was today we're finishing up periodic trends, and then I'll give you guys some time to get in your little like part 4 groups to talk about your 5-minute talk you're going to give tomorrow. Remember that question you selected? Okay, it was supposed to be today, but we didn't get to touch that Friday. So you guys will have some time within the class to do that. And then tomorrow, you guys will have your 5-minute little talk. It's a low stress situation, it's just a conversation in class. So some of the conversation pieces might be your opinion, or it might be some research you found. People are going to be listening and going, great, and giving me that positive feedback. And also tomorrow we're going to do some nuclear chemistry, alpha, beta, gamma stuff. And then Wednesday we have a lab. It's called Skidlium. I think you got that one now, okay? So it's called Skidlium. We're going to talk about radioactive decay of Skittles. And then you'll have some time to finish up if you have any questions of your group project, your scientist projects. Your scientist projects are due on Wednesday, so I can look them over before you present them in small groups on Thursday. So Thursday, you guys will have, a 10-minute spiel probably about your scientist project. You don't have to read every detail, but you should know your stuff so you're not sitting there staring at the screen while the rest of the class is over here and they're trying to listen to you talk to the wall. Okay? So do know what you're talking about so you don't, embarrass yourself. And then on Thursday, we'll take the multiple choice part of the test. So that Friday, you take the free response part of the test, because with Friday being a little short, I didn't feel comfortable trying to slam that together in one class. And if you find you're not unsure of things, Thursday, what should you do before Friday? Study those things. So it's actually to your benefit either way. Time and making sure you know concepts. Okay? Thanks. I got one head shake. Anybody else? All right, cool. All right, so effective nuclear charge shielding effect. We know at least the terms. We're going to apply them now, okay? So you guys, this is so weird. You guys already have the knowledge of how to think about the atomic radius and why it changes. So now we're going to talk about those two factors and talk about applying those factors in context to the radius and then so forth. So what is nuclear charge? What's it referring to? Give me something. Shout it out. Nuclear charge. What's in the nucleus? What gives it charge? Protons. Okay, so if I'm going across, let's choose one period to work with. Anybody? What's your favorite period? Period 4. Who's that start with? K. All right, so here's our group 4. So, not group, period 4. And if you have period 4, how many protons does potassium have? Everybody has to have a periodic table in front of them working with me. How many protons? So potassium has, you're good, you're looking at sodium. Okay, so potassium has 19 protons. How many energy levels are around it? 4, because we're in period 4, right? And the energy level is essentially a period of, it resembles a period as you go down the periodic table. So I could draw this with 1, 2, 3, 4. Okay, now it's all over my text, but that's cool. So we have our 4 energy levels there. How many protons does bromine have? Bromine. Say again? 30. Am I on the same? Okay, I am. 19 to 35. Okay. So there's 35 protons. Okay. How many energy levels does bromine have? 4. Why? We're in the same period. Okay. 4 energy levels, 4 energy levels. However, as you go across the periodic table, you're gaining electrons, 1, and you're gaining internal. I have a granola bar by now. Okay. Okay. So also you're gaining protons in the nucleus. Yes. I am drawing a really elementary atom here. We know that they look like spheres, dumbbells, double dumbbells, and flowers. I'm drawing it just for the effect of we know that there's this distance that's occurring throughout.
Yeah, like for the transitions, like
So it goes from 4 to 3. Yeah. So when I draw bromine, I would see first energy level, second, third, fourth, which is 4s2, and then 3d10 would be on the inside, and then 4p5. So it's only inside, you're right, but I'm just drawing the fact that they're available 4 energy levels total, not 5, not 6, just maximum of 4. Good question there. Okay, so the story here is same number of energy levels. I know that there's different valence electrons out here, but what's really happening here is the nucleus is trying to maintain some attraction. So the protons here are trying to attract its outside electrons, its valence electrons. Same thing here, 35 protons attracting the outside electrons. Who do you think is going to do a better job of that? Why bromine? 35 whopping protons versus 19, right? So 35 charge, positive charge, is really going to pull the outside shell in simply through attraction. So it's called the nuclear effective charge, labeled ZEF, but it's really just about protons attraction for the, I'm just going to say the valence electrons. So if protein's going to do a better job of attracting, what do you think it's going to do to the size of bromine? It's going to get smaller simply due to attractive forces. So this one's going to shrink a little bit as it continues to attract its electron clouds. So bromine is smaller than potassium, which is larger, and we do that comparison on the same period, which eliminates any chances of trying to confuse nuclear effective charge with shielding effect, which we're going to get to in a second. Yes, sir?
So for the proton, I guess for the attraction, it's because the protons weigh so much more? Or, I mean, the electrons also weigh,
It's not 100% correlated to mass. It's more connected to their magnitude of charge. So a 19 plus charge is going to attract some electrons. A 35 proton or plus charge will attract many, many more electrons with a much stronger force. It's basically like a weak magnet and a strong magnet. Like these neodymium ones here, neodymium, you guys know what neodymium magnets are? Okay, it's gonna stay. But if I throw a ceramic magnet, let's see if I have a ceramic, I don't believe in those weak things. There it is, a weak thing. So if I throw this weak one, no promises, I might just break this ceramic one. Okay, it tried. It really did. Yeah. Okay. But the neodymium one, I can throw it. It's rolling, but it's still there. Okay? So it's more about the magnitude of attraction. All right, you can buy those on Amazon. All right, so coming back here, we talked about a period trend, which is nuclear effective charge. What's the group factor we spoke of? The other factor. Say again? So the valence electrons are there, but what's between them? What's between the nucleus and the outside? Say again? Orbitals with electrons. Okay, so it's called the electron shielding effect. So if I have, let's say potassium, which you guys had 4 energy levels, right? Now let's do one higher in group 1. Let's do lithium, just because I don't want to draw a lot. Okay, lithium has how many protons? 3 protons. How many energy levels does it have? 2. 1s2, 2s2. I'm just drawing them as orbitals or orbits, as Bohr would say. So comparatively, who has more energy levels? Potassium or lithium? Okay, so who's bigger? Okay, because 1, the sheer size is because of the energy levels, but 2, it's also because which nucleus is closer to its valence shell? Say again? Lithium, that's only 2, it's like literally, here's a nucleus, it's attracting, boom, there's its valence electrons. Whereas potassium's like, I don't even know I have valence electrons, they're so far away. It's like going through 5 states to say, oh, here's my long lost love of the electron. So there's a lot of shielding there, and it's shielding the magnitude of attraction. So if I have a magnet, oh, my husband just got these cool magnets. Okay, so if you had a magnet and you had a piece of paper, magnet number 2. Santa, you must come down. Okay. So Oh my. Be my new please. Thank you. Okay, attract my valence electrons. Oh. Okay. Oh gosh. No shielding whatsoever, right? Take it off. Okay. But energy levels. Look at all these energy levels. I hope it doesn't work. Okay. Oh darn, okay. No attraction. It's simply because of the shielding of the valence electrons. Got it? Okay, so thank you, dear. Alright, so that's basically going to be the same exact explanation for every trend. It's just, you have to know what the other trends are and be able to explain why does the radius affect the other stuff you're talking about. So the only other two I'm going to address for now are the size differences between ions and then also ionization energy. So, you guys tell me, raise your right hand if you say cations are bigger or anions are bigger. Right hand, cations are bigger. Left hand, anions are bigger. Right hand, cations are bigger.
That's your left hand.
I'm sorry, I'm trying to mirror you guys. Whenever I have to teach, sometimes I'm mirroring you. Left hand if cations are bigger. Right hand if anions are bigger. I can teach chemistry, but left and right we're still working with. Okay. All right, so I do see a pretty good number saying cations. Okay, let's talk about this. If I am, let's just do lithium because it only has 3 electrons, right? Draw lithium. Draw it for yourself. There's good old lithium. And then I'm going to draw it like a orbit model, even though we know this is not 100% right. How many electrons are in the 1s orbital? 2. So draw your 2 little electrons there. And this is exactly how you saw it on the simulator, so I think this will make sense. How many how many electrons are in the 2s energy level? 1. So that's 1s, 2, 2s, 2s1. Okay. Make it an ion. What's lithium going to do? Gain 7 electrons to become octet or lose 1? Lose 1. And I know it doesn't drop back to octet, but the word octet can mean just stable shell. And so a stable shell is going to be something that's a full shell. So the 1s2 is the fullest it can get, right? It can't have any more. So when you lose an electron, what does it look like now? Without the what? Oh, without the last shell. So is it bigger or smaller? Smaller because it lost the valence electron shell. So comparatively, does lithium with a 1+ charge have a larger radius? Thank you. A larger radius or a smaller radius than its parent? And when it came from? Smaller. Okay, so lost electrons, the atomic radius is smaller. And you guys can do the anion one. Write it down. Draw a picture for one of those. You guys draw an example. Do a small atom. I should see you drawing for an anion. Thank you guys. All right, what's your anion you guys selected? Give me something who would want to gain an electron. Fluorine it is. Okay, fluorine has how many, what's its shell model look like? 1s2, okay, 2s2, and I'm going to pretend the 2s is just the same level. 2p, 1, 2, 3, 4, 5. Okay, so 1s2, 2s2, 2p5 is fluorine, or just drawing it with 2 energy levels in general. So how many valence electrons does it have? Say again? 7. 1, 2, 3, 4, 5, 6, 7. 7 valence electrons. it would pretty much be dumb to take away all 7 to drop it back down to the inner, the electron count of 2. Instead, what's it going to do? Okay, so it's going to gain or add 1 electron, and where's it going to go? To the outer shell, which in this specifically what I'm referencing is 2p, and it'll be 6 instead. So I'm going to draw this as 1 green one here. Okay, so far it doesn't really look like anything has changed. But what you have to realize is that fluorine by itself is just a stable little guy. It has a whole electron cloud with all these electrons. What do you think is going to happen when I put another negative electron with all of these other electrons that are here? What do electrons do with each other? They repel. Okay, so if you have some repelling or repulsion going on, think about if you repelled from somebody else. What would you then do with your whole little bubble of people? You'd expand, right? Same thing happens here. You have an electron cloud, it's got one size. When you add another electron in there, repulsion occurs. It blows up just a teeny tiny bit, but still, anions, every single time when they gain an electron, they will get larger. Atomic radius is larger. Whereas cations, which lose the entire outer shell, they have to get smaller. So it's fine to memorize that, but it makes much more sense to understand it as to why that occurs. Okay? The last thing I'll talk about for now is ionization energy, which is the second part you guys looked at. Caleb, we talked about this. Do you remember what we talked about ionization energy being?
The energy to lose or gain an electron.
Okay, I'm going to stick with the losing, okay? So if I'm losing electrons, guys, what am I making? Cations, right here. Perfect. Thank you, sir. All right, so let's say you're very greedy for cookies, okay? And I came to you and I was like, William, I want that cookie. How much energy am I going to have to put forth to steal that cookie from him? I mean, a lot. I'm going to have to fight him for it, okay? So I'm going to have to put forth a lot of energy because he has 7 cookies and he doesn't want to give up an electron. I mean, a cookie, aka electron. Okay, what if Zach over here was like, meh, 1 cookie? He's like, I like brownies, not cookies. It's fine. How much energy is it going to take for me to grab that cookie from him? Not much, because he's going to be like, meh, you can have it. Okay, so those are representing electrons, right? So he doesn't like cookies, but he does like cookies. What I'm actually saying is that one of them wants electrons more due to octet, meaning its proximity to octet. So if you have 7 electrons, are you going to give up an electron? Heck no, right? It's going to require a lot of energy to get that from you. If you've got 1, 2, 3 electrons, what do you think about ionization energy? What do you think about the relative magnitude? Lower or higher? Say again? Lower. Okay, so 4 is the break point, right? So if you have 3, 1 through 3 valence electrons, it's going to require less energy to take your electrons because you're, relatively not close to octet. You're fine to lose those and become cations of a +1, +2, or +3 charge. You're like, that's totally fine. But if you have 5, 6, or 7 valence electrons, by golly, you're not giving those electrons up. You're putting up a fight for those because you're so close to 8. So it's going to require more energy to do that because it's not likely that you'll be giving up those electrons very easily. So does that kind of logic make sense? Based on octet. Shake your heads, people. Something so I know. Even if it's a shake no. Because I try to make sure I gauge you in class because I have to quiz you because I really don't know unless I hear from you how you're doing, okay? So in terms of that, that's based on our valence electron count. Well, then sometimes you have to compare, like, based on distance from the nucleus. So do you, thinking about our whole attraction thing, I think Omar was my one showing the shielding effect. Do you think it's easier to take an electron from potassium, which had 4 shells, or from lithium? Who's holding on to its electron more? Why? Okay, good. So it's got a lesser shielding effect. So if you have a lesser shielding effect, meaning your protons are doing a pretty dang good job of attracting your electrons, does that make the ionization energy higher or lower? Higher ionization energy, because it's going to have a lot of energy required to ionize you, to take your electron. And I'm comparing lithium and potassium because they're in the same what? Group. So again, group trend, shielding effect. Period trend, or period factor, what was the other one? So the two factors you wrote down last week on Friday, shielding effect is what you talk about when you're going down a group. Effective nuclear charge is what you're talking about as you go across a period. All right, so I'm comparing these because they're in the same group. Potassium's nucleus is in here. What's happening here? Right, it's so far away it doesn't even know it has a valence electron, so it has a great shielding effect going on, meaning it has high attraction or low attraction for its valence shell? Low attraction. And if it has low attraction, its ionization energy is lower because it doesn't put up a fight because it's not strongly holding onto the electron anyway. So I can just pluck it off really easily. Despite the fact that both of these have how many valence electrons? They both have one valence electron. So the logic that made sense, like, yeah, it's going to require less energy in general for the blue part over there. That's just comparing the valence electron counts. But when you're looking at individual atoms, you do consider their distance from the nucleus because it makes a difference. Okay, so I'm going to have one more example with this, but dealing with the shielding effect, and then I'm going to be done. Yeah.
So the noble gases always stay.
Yeah, they're not going to likely because they already have octet, and so they have a really, really high ionization energy. It has a lot of energy requirements to take an electron from it. All right, last one is fluorine. So I'm doing these because it's the same example. Fluorine is not in the same period, but it is with who? Lithium. Okay, let's do lithium. So lithium has 3 protons, as you guys said earlier. Fluorine has 9 protons. How many energy levels? 2. Oh, I didn't draw 2 there. There's 2 right there. Okay, so 2, just the same as lithium. Who's smaller? Lithium or fluorine? Don't look at my drawings, they're not to scale. How are you thinking about that? Okay, or we have our normal trend here, but it's also because it has more protons. So this one is a higher what? What's the term for it? Zeph, higher Zeph, which is higher effective nuclear charge. If you have 2 energy levels as lithium and fluorine both do, tomato, tomato. You can't really compare. I mean, you can't really see any differences there. But this one has 3 protons, whereas this one has 9. So that has a stronger attraction within that same radius. So 9 protons wins the attraction battle. So it's going to require a high amount of energy, meaning higher ionization energy, as compared to lithium. So they're both high, but this one's higher due to the greater attraction that the nucleus portrays. All right, let me stop for a couple minutes. Switch modes, PS6. I want you guys to talk about some of those examples, and I'm going to come around for some questions. I'll give you guys about 15 or so minutes to work on this.
Only thing I got confused about was the electrons and
The last thing, I know some people just asked me this twice. Most metallic follows exactly the same trend as atomic radius, as you can see on the board. It follows that left and then down, which basically ends up being a diagonal. So the most metallic element on the entire periodic table is what? Francium, and it means likely to lose electrons. Why is francium likely to lose electrons? It has one valence electron and it's humongous. It doesn't even know it's got a cloud of electrons way out there. So it's like just going to pop that electron out, no problem at all. Low energy required to do that. All right, so continue doing what you're doing. Yeah. Yes. So francium would be the most reactive. Yes. Because in terms of the word reactivity, we just keep saying it. It just means likely to exchange electrons with somebody because then it forces a reaction to occur. So it's really based on the electron. Well, you have 2 minutes.
Yeah. Well, it decreases. Silicon is a second. So that melts. That's how you that would be able to tell you
So it has less valence.
So, as a quick note to self, I know some of you guys are not engaging in your groups very well. Don't sit there and look pretty. You guys can move on to looking at unit review if you're not going to look at the periodic trend. So some of you guys are doing fantastic, and I'm very much applaud you for your collaboration.
Oh, I used to use the
We don't do one. I was confused. It's not like alkaline, it's like
You're still 1, 2, 3 for those other kids, and then this is the only one that applied. That's why for B.
All right, eyes up here for me. In 5, 4, 3, 2, 1. Thank you. Tell me which columns should mirror each other. Should be exactly the same because they're following the same description and the same trend. Mikado.
Most metallic and largest radius.
Okay, so most metallic and largest radius both run which direction? Increasing which way? To the left and down. And that's because I just told you most metallic. What does most metallic mean again?
It's like
I just wrote on the board. But so you guys are describing which is the most metallic, but what does the word metallic mean? You don't know this, write this down, okay? This is a descriptor. Most likely to lose electrons. That's like incredibly, that means that they're incredibly reactive. They're very, very, very likely to lose electrons. Meaning they are just willing to give it up at any point in time. So that means they're most metallic. Okay, back here. Most metallic, largest radius. There's one more that runs, that should be this as well. Frank.
Lowest electron voltage
lowest electronegativity, because when you're doing your electronegativity hand like this, where's lowest at? At the crook of your hand, right? Right where your fingers are. Okay. So first, second, and fourth should be the same, and then highest ionization energy should be the same as highest electron affinity. So how many elements should really be in here? Two, like two that are, one that's most metallic, largest radius, and lowest electronegativity, and then another one that's these two. There are 4 to choose from. You will not be using all 4. There are 4 here, but you won't be writing them all. All right, so I have a couple more minutes with you guys. I have about 15. Here's what I'm gonna have you guys choose to do. Give me 1 second, Jacob. Thanks, guys. So, in working in your discussion groups that you'll be presenting with tomorrow in a 5-minute discussion, you guys have some time right now to move there. And then secondly, you can see from homework, finish the S6 who's basically done with problem set 6. A large majority of you, great. The last thing is called close reading. So if you've ever done close reading in English, this will resemble it. But before I kind of leave you for the day, you guys have a series of articles at your table. Please make sure everybody gets one. So I made a couple people in charge. Make sure everybody gets an article right now. Put your name on it. You are going to be the expert witness on this information tomorrow. So, where do chemicals come from? Fusion at work for sun, and then antimatter. There are 3 article types. And I'm going to pass out this little sheet called close reading to you guys. But basically what I'm expecting is that you're taking some time to slow down the reading process. When you slow down the reading process, you start to see words that are unfamiliar. You start to think about the connection. You start to say, oh, this is that reason why I made this question in my head and I'm reading it further. So in this little description, it basically says it's worth 10 points. 6 points is basically annotating your text, meaning underlining, highlighting, writing out key phrases, writing out thoughts, highlighting words or circling words you don't know and defining them. So you need to make at least 6 really good annotations through accumulation of those, and I'll hand this up to you in a second. The next 2 points come from a summary statement that's 25 words or less. That means that you are taking together all of this great information and pulling it to an understandable fashion in 25 words or less, versus yapping at us forever. And the last 2 points come from a reflective statement like, I realized this, I'd like to know more about this, I remembered this, I noticed this. So it's a reflective component. So that's for homework, highlighted, annotated, and so forth by tomorrow, okay? All right, get into your other groups. Keep going on that part 4.
For the unit briefing, there is the question was asking for and then when I changed to a form, would you just turn it to the line?
Yep, that's how you write the indices. Perfect. If you're looking for the link, it's under Friday. That's your periodic trends properties group.
Might be in there might be a link in the video.
Can you see of that angle? Okay, it increases the same as atomic radius. So metallic we don't speak of as a trend per se, it's just a property. And so it probably makes sense. All the metals of periodic table, let's face it, those are all the metals. Most of these over here are non-metals, so it makes sense that metallic nature increases this way towards the metals. But it happens to follow the same, as the atomic radius directions.
Is this too much?
I can go back.
Have you guys already discussed your partner talking to you? Did you guys introduce him? This is my last chance to make sure you know what you're talking about tomorrow. Raise your hand if your group has divvied up who's speaking about what in your 5-minute talk. Okay, no one's divvied up? Okay, we have one group. So if you have 5 minutes at least, everyone should talk probably for about a minute or so. And then you as a professional presenter, you're not staring at the board. You're not staring at your the text in front of you. Try to speak from the heart and from the mind a little bit.
I guess I'd be like